Okay, so we'll start with programming with Clingo. This is actually the new handout. If you go to the Blackboard, there is a file called pwc.pdf. And as I said before, the lecture note that you just studied for today's quiz is about the theory of stable models. And this is more like practice of the answers at programming. And you could have started this one first and then come to the stable models. And we just chose the other way. And obvious question is, why then we bother with so-called stable models with all this negation and reduct, and what is actually the intuition here? So we are going to talk more about that when you go into the programming side. So just try to remember the definition of stable model, and time to time I will connect to this. Okay. So obviously, you already know what is the program, what are the stable models. Basically, programming with Clingo is just to compute the stable models. Okay, so you just need to encode some program in some ASCII notation, and the Clingo find the stable models, and that's all you need to do. If you remember the beginning of the semester, I showed you the declarative problem-solving method, where you encode the problem as some representation, which is in this case is a logic program, and then you use some answers, some systems like answer solver to find the solution, which correspond to the solutions of the original problem. Okay. Now these solutions will be encoded by stable models. Okay. Most of the time, the solutions that you are looking at from the original program will be reflected in the stable models. Right. So this is just notation in ASCII characters. So you have these things. So one thing to be careful though is the Clingo understand integers. Okay, it does understand certain non-integers, but let's just focus on the integers for now. So what happens is when you have two integers m and n, when you divide, then the result may not necessarily be integers. In this case, you are taking the floor of that number. Okay, so largest integer that is smaller than that particular result. So we have two symbols related to the division. So quotients and the remainder can be found by each of these symbols. And we also have the exponent where we have this double star notation. And the other things are something that you already saw. For the historic reason, the negation symbol is encoded as NOT. Okay, and comma is somewhat challenging to remember. So when the comma is actually used in the body, it means a conjunction. When it's used in the head, it means disjunction. Okay, and there are some special atoms for bottom and top, which is found false and found true. Okay, so this is just a notation. So let's revisit this simple example. So the example here was to find out what are the warm cities. And according to this particular program, warm city, C, was defined as a city that has a temperature higher than Austin. Okay? So this reflects the basic idea of database reasoning. The database, like this table, can be encoded in this line. Okay, so you can encode the fact as these simple rules. Okay, so there are actually 4 rules here: 1, 2, 3, 4. Okay, now the other one is the rule here, where you can derive new information not explicitly stored in the database. So we assume that C is warm if C's temperature is T1, and T2 is the Austin's temperature, and T1 is greater than T2, then C is called warm. So intuitively, C is warm if the temperature in C is T1, the temperature is in Austin is T2, and T1 is greater than T2. So this is just a reading of these logic rules in terms of English, and you should be able to do this, right? Now, when you find these warm cities, note here that we are not describing algorithm to find it. We just declare what are the warm cities, and it's up to the Clingo to find the solution. So you are, of course, there are actually the solving component of the Clingo, which we are not going to talk today. Okay, so we'll first focus on how to represent this knowledge in the language of Clingo. Now, how actually Clingo find the solution? That's actually, you already know some part of it when you remember the DPLL algorithm, right? That find the solution for any propositional formulas. Some tweak of the DPLL algorithm can find the stable models too. Okay, if time permits, we'll go into that, but that's actually quite more complicated than DPLL. So I'll just probably put some pointers for some of you who are interested in. Okay, so then now the next homework for you is actually to run the Clingos. So pwc.pdf file, the lecture note, the next lecture note has many exercise problems, and you will be able to use Clingo to run these things. Okay. All right. So the command is actually simple. You give the name of the file, Clingo, and warm.lp is the name of the file that stores the previous program. Okay, those two lines that I show you. And if you type in, it's a command line execution. So you type the name of the command and the file name, and Clingo returns this answer. Okay, so maybe let me show you if I can do it here. So first, this is the file, okay, and nothing to do. I happen to have multiple versions of Clingo, so I'll type Clingo 5 as a name. But if you just download most recent version of the Clingo, you can just type Clingo. Okay, so this is the output of the Clingo. As you see, I don't know what this current version, maybe it's a bit more than 5.2.1. It doesn't matter. As long as Clingo 5, it will have the same program, input program. So now what is Clingo doing? It reads the program and it solves. So there is actually one answer. This answer is actually the stable model. What Clingo does is actually just return the stable models. Now when I type this one, I just give the file name. Sometimes there are multiple stable models, then you can actually put 0 at the end. So in that case, Clingo will return all stable models. Now note here that this actually has only one stable model for this particular program, so it doesn't actually return more than one. Okay, but if you're interested in for some problems that you want to solve that has multiple solutions, you can type some numbers. If you put the 0, it asks Clingo to find all solutions, return all solutions. If you use less 3, then you ask Clingo to find 3 solutions. Okay. Now, something that you might encounter when you do the program is so-called unsafe program. And you will encounter that Clingo cannot compute this program. Clingo complains that this program is unsafe, so it does not know how to do. Now, the program here is unsafe program. And the new rule is the last one, right? So this rule is so-called unsafe. So what is the safe program? The complete definition of safe program is a bit more complicated, but for now, when you talk about the programs with this form, basically what it means is the variables that occurs in the rule must have an occurrence in the positive body as an atom. Okay, so it should be in some atom in the body that is not preceded by negation. And the Clingo program is called safe. Now, when Clingo finds unsafe variables, then it complains. Okay, now let's look at why this is the case. There is a T occurring here. Let's actually go from the beginning. So let's look at this rule here. Okay, So there are variables C, T1, and T2. Okay? Now C occurs here and here. Now when C is in the rule, for the program to be safe, or for the rule to be safe, this C must have an occurrence in positive body, which means it should be in an atom in the body that is not preceded by negation. So the C here, there are two occurrences, and this occurrence makes C to be safe, make this rule to be safe with respect to C. Okay, because C has occurrence in the positive body. Okay? Actually, to be precise, it's an atom in the positive body. What about T1? Of course, T1 occurs here, and this is already a good occurrence. What about T2? T2 occurs here and here. This is not a good occurrence, but this one is a good occurrence. Okay? To make this rule to be safe. Now, T1 is greater than T2 is not an atom according to the Clingo terminology. It's called comparison. So comparison doesn't contribute to the safety. Okay? So the rule here, so it's a safe program. All variables in the rule must have an occurrence in the positive body, which is in some atoms in the body that is not preceded by negation. Only then the program is safe. Okay? Now, why the last rule is not safe? It occurs in two places, T and T here, right? This is not a good occurrence, as well as this is not a good occurrence. Okay? So this is not safe. What is the intuition about safety? When program is safe, Clingo knows how to ground this program so that it generates only finite number of ground rules. The propositional image becomes finite. But when the program is not safe, then the propositional image is infinite. Why? We actually saw last time when we consider only these two rules, we can only consider a finite number of propositional image rules, right? That we saw. But now when we add this, what happens to the propositional image? So let's say H hot temperature. This rule, when Clingo turns into propositional image, it will actually generate multiple rules. So for instance, 101, 102, 103, so you get the idea, right? You can go on, and it never terminates in generating the propositional image. So this is not a good thing. Yes?
So what if you did not T less than 100, less than 100?
The same thing.
The same thing?
Yeah. Because not T less than is still another good occurrence. Good occurrence should be an atom in the positive body. Okay?
What if we had T greater than 0 and T less than 100?
Pardon me?
T greater than 0 and T less than 100?
Yeah, that's actually another case that we have to bind. Yes, that's actually the safe. Okay? So if you can bind this T to certain range, that is okay. So here is actually the thing that I just say. The definition here that I just said is actually not complete, and I'm not going to give a full definition of safety. Okay? The reason is when we introduce more construct in the Clingo language, then the safety becomes more complicated. And basically, you don't actually need to know those complex notation, definition. Okay? So one thing to remember here is when the Clingo program, when it runs, it complains that the program is unsafe, then basically what it means is the propositional image may be infinite. So Clingo cannot generate a finite number of rules. Okay? So something wrong with your program, and you have to give more information to the Clingo so that it can generate only finite number of rules. Okay? And that's actually easy to do. Okay? You can just put some atom in the positive body or some intervals to specify the range of those numbers. Okay? Okay, so we will come back to, yeah.
I didn't get this line. Some atoms in body not preceded by one.
Atoms in the body. So there are atoms in the body. These atoms are in the body, and they are not preceded by negation. You don't see the negation in front of this atom. That's what it means.
And then how do we say, like, we saw that this example, like, we take 1, 0, 1, 1, 0, 2, and so on. But here there is no negation in the body, right?
So it should be in the atom that is not in front, not preceded by negation. So what are the atoms that is not preceded by negation? Let's actually look at this. So let me. So let me ask you from the second rule, what are the atoms in the body that is not preceded by negation? What are they? This one. This is an atom in the body that is not preceded by negation, right? What about this one? That's also the case. So there are two atoms in the body that is not preceded by negation. So this rule is actually safe because all the variables that occurs in this rule occurs at least one of these atoms. Okay?
Even for third rule, we have, like, positive values.
In the third rule, we don't have that atom. This is a comparison. Yeah. Okay? All right. Well, the definition is actually not complete, so you can actually a bit more general, but let's not bother on this side. Okay? The reason that this occurrence in the positive body makes sense is when Clingo generates the propositional image, lots of those atoms will be replaced by bottom, right? And those atoms replaced by bottom can be thrown out. So even if the propositional image, by definition, it is infinite, Clingo can only consider some subset of those propositional image. Okay? And that subset is actually finite. Okay. There's some other tricks, like pooling, which is not very theoretical. But if you have to repeat many atoms, you can basically write only one atom. So if you have this table that you saw before, you can just write one T with those semicolon separated list. Okay? This is just some convenience. Okay? All right. So here's one exercise from the lecture note. So what is this rule doing? Child xy if parent yx. How would you read this rule?
X is child of y, y is parent.
X is a child of y if y is a parent of x. Yeah, that's actually a natural way to say. Now, if we run the Clingo on this program consisting of this rule with the fact. So the fact is N is the parent of Bob, Bob is parent of Carol, and Bob is parents of Dan. So in terms of family hierarchy, there's an N here, Bob here, Carol, and Dan. So what will be the stable model in this case? What do you expect to be the stable model?
There are three new facts.
How many stable models will be there?
One.
This is a positive program, right? So obviously the minimal model here should contain all the facts, as well as the fact implied from the fact, given fact using this rule, right? The rule allows us to derive a new relation about the child, which is actually the kind of opposite to the parent relation. Okay? So obviously the answer set or stable model will be all these five together with child of Bob N, child of Carol Bob, child of Dan Bob. Okay? So that will be the stable model. Good. So let's do a couple more exercises here. Now, given this, how do we define grandparent in terms of parent? We did something similar to this in the homework, right? With first order logic. How do we define grandparents in terms of parent? Can anyone suggest?
So just the grandparent or put together as
Grandparent here.
so we have two parents in the world.
So how do we define grandparent in terms of parent?
X is the grandparent of Y.
You have the two parents. You have to introduce one variable.
New
Just say the rule, please.
So, if grandparent XY,
Grandparent XY. Here.
parent XZ,
Uh-huh.
parent ZY.
Yeah. So I have a similar rule here. So grandparent XZ. If X is a parent of Y and Y is a parent of Z, then X is a grandparent. So this is actually easy to understand, right? Okay. How to define sibling in terms of parent?
Sibling XY if
Okay. Sibling XY if
parent
parent
XZ,
XZ,
parent
parent
YZ.
YZ. Is it? Okay. Let's do so. So sibling XY. Can you say it again?
If parent, some common parent,
Just say the rule. There's no common in the language of Clingo. So
parent Z of Y,
parent ZY,
parent ZX,
GX,
X not equal to Y.
X not equal to Y. Okay. So yeah, that's what I had here too. Okay. Yeah, so they have the so-called common parent, which is not explicit here, but this parent is actually Z, right? So Z is the parents of those X and Y, and also you have to say that X and Y are distinct objects. Good. How do we define ancestor in terms of parent?
Recursively.
Okay. How do we define ancestor in terms of parents?
Ancestor XY.
Let me select one person. D Xiao. Do you have D Xiao? Okay, so how do we define ancestor in terms of parent?
Ancestor XZ,
Ancestor XC
if
if
parent
parents
XY
XY
and parent XY.
and parent XY. Why do we repeat parent XY here?
That's one.
This is one. That's it. Now, so this rule, are you satisfied with this rule? By the way, this rule is actually unsafe because this Z does not occur in the positive body, right? So maybe we should throw this out. Maybe Shang Yu.
We just added an ancestor Z1 or YZ.
Okay, just spit out the rules.
Ancestor X of Y if X of Z if
Ancestor XY or ancestor XZ? Which
yeah,
one?
anyway, like if
No, just choose one.
XY,
Okay.
then if parent XZ, then ancestor ZY. And
Ancestor of ZY.
Yeah.
Okay. That's it?
Yes.
Okay. So are you talking about these two rules together or just this rule only?
One.
Okay, so we don't need this one. Okay, let's pause here. So ancestor xy if parents of xz and ancestor of zy. This completely defined for this ancestor. True or false? False. Why?
There is no ancestor to start with.
So what we need here? What
The
do we-
rule that we deleted.
Huh? So just say the other rule that you need.
Yeah, so if it is parent, then it's also ancestor.
Just read the rule.
AXY,
AXY
if PXY.
if pxy. The previous rule was almost, but it used c instead of y, so this was rejected. But if we have these two rules, okay, so we can define, this is actually the base case. So ancestor is a parent, okay? Although it might be a bit weird that you call your parents your ancestor. But anyhow, that's how the user definition goes, okay? Now, this is the base case. And there's a recursive case here. I is recursive because A occurs in both left and right. Okay, so if X is an ancestor of Y, if X is a parent of Z, and Z is an ancestor of Y. And in fact, you can do a bit different ways too. You can actually use two ancestors here, and it does not matter. This actually are equivalent program. So the rule is saying that X is ancestor of Z if X is ancestor of Y, and Y is ancestor of Z. Okay? Yes?
In Clingo, does the order of the rules matter?
No, does not matter because by definition we define the program as a set of rules. By definition, set doesn't have any order specified. Okay? So if you just write this one first, if you switch the order between the rules, Clingo's output is the same. All right, so that is how we do. Then can you imagine what will we get with respect to the previous one? So we had this family relation, and if we add all these things, who are the siblings? So let's go back. Who are the siblings here? Carol and Dan, right? And how many ancestor relations do we have? 5. So we see 5 ancestor relations, right? And Bob is one relation. Bob Carol is another. Bob Dan is another. And Carol is another. And Dan is another. So we have 5 relations. So if you are in doubt, of course you can run the Clingo program. So here, this is child. So I've typed the program here. Okay, so this is the program that you saw before. Okay, and type Clingo 5 and child LP. And let's just say return all. Again, there's only one stable model for now, and this returns all the family relations. Now, let's think about it. We talk about the definition here, right? Now, one of the things about the minimal models help here is the definition. So definition usually goes like this. This is true if this condition is true and nothing else. So usually we don't articulate that nothing else, but when we define something based on some condition, we say that this is the complete characterization of the definition, right? So here, when you talk about the stable models, it helps us to write this definition very succinctly. Okay? All right. Now let's look at arithmetic. So this is the rule that you can read now. So n goes from 0 to 10. Now the Clingo understands this as 11 rules, where n is replaced by 0, 1, 2, up to 10. So one of the rule it will generate as a propositional image is 0 and 0 star 0 plus 0 plus 41 top p of 1, 1 plus 1 plus 1 plus 41, and so on and so forth. Okay. In other words, you are generating the polynomial of on n, where n changes from 0 to 10. What are the values of what are the values of this polynomial? Okay. So if you do that, so you can just type Clingo and let's name this file as quadratic. So it returns this solution. Okay. So when n equals 1, the polynomial here will return 43. Okay, because 1 plus 1 times 1 plus 1 plus 1 plus 41 is 43. And if it's 2, it's 47, and so on and so forth. Okay? Easy. Now, sometimes we want to have a more general polynomial. So the coefficient here is a and b and c. So previously it was just 1, 1, and 41. And we can write some placeholder a, b, c here. Now these placeholders will just keep some value, and how do we specify this value is in the command line. Okay? So the same program here, and you call this these option. So dash c means you're given the value for these placeholders. So a is now 1, b is 1, c is 41. Then it will operate the same as in the previous file. But it could be more general if you change the coefficient for a, b, and c values. Okay? And of course, note here that n is actually also the placeholder. I can also change the range here. Yeah? Now, there's alternative writing, which is instead of giving this as a command line, you want to put this thing in the file. Then what you need to do is to have this pound thing. So pound const a equals 1, then you don't have to give the command line constant. Okay? All right, so what Clingo understands is an integer. So then the question is, what is actually the stable models of this program? Pm comma n, when n is from 1 to 4 and n equals n is 2 times m. What will be the stable model here?
This is unsafe.
Okay, this is kind of the corner case that the previous definition does not cover. It is actually the safe because the reason is this actually gives the bound for this m and n. So it does not need, it does not generate infinitely many rules. Okay?
And what was the comparison instead?
Yes. So that's what I said. The previous definition was not complete. It does not capture this space. Yeah. So, but you can actually easily see that why the propositional image is finite in this case. So let's try to do that. So this body is only true when n is going from 1 to 4. When n gets the value other than the number 1 to 4, then the body is bottom. So that Clingo does not need to consider that rule. So there are only finite number of rules that the Clingo have to consider. So this is why it's actually safe. But obviously, the previous definition, the syntactic definition, actually didn't cover this case. Okay. Yes?
Well, this is more of a question of curiosity. In terms of like runtime, like running a Clingo program, Clingo's figuring out a model for this and it's determining a value for m. Is it like brute force, or does it have like some sort of heuristic?
Good question. We can spend one semester to develop the algorithm. In short answer, it's actually very, very fast. Okay, for most of the methods that we do. What about the search algorithm? Does it use brute force? No, it doesn't. Okay, so something to distinguish between what I explained theoretically here. Clingo really does not generate all the numbers, all the rules, one by one. It actually does very optimized generation of the ground rules. Okay? And you will actually experience this when you use Clingo to do some combinatorial search problem. It's actually fine very quickly. Okay? Although there are some problems that one cannot solve, because basically what Clingo is solving is at least the NP class problems. Okay. All right, but let's just focus on the current problem here. So what is the stable model here?
P1 to P2.
Okay. Is it true? So the answer is P1, 2, P2, 4. This is only one stable model that the program will have. Let's check it. So we can try to generate the rules. So n goes from 1 to 4. So let's say n equals 1. Okay, so then this becomes top, right? The next one is n equals 2 times n. And in order to do that, n must be what? 1/2. But 1/2 is not something that Clingo understands. So Clingo throws out that rule. So when n equals 1, this will not be, the rule will not be generated. Now then, when n equals 2, what is m? M equals 1, because 2 times 1 equals 2. So this is actually true. Okay? The assignment of m and n that satisfy this, as well as resulting in integers. That's only when n equals 2, m must be 1. And similarly, you can do when 3, again this is a fraction. Okay? So this rule will not be generated. When the next one is 4, then m can be 2. So this is it. So the Clingo will generate only these two rules from this program. And obviously the stable model here is P12 and P24. There's only one stable model containing these two atoms. Okay? I should. So actually, Clingo is quite sophisticated program. In fact, it allows certain real numbers as well. Actually, in my group, we also worked on extending the idea of ancestor programming to handle real numbers so that we can model the continuous changes, continuous dynamics. But in this class, we are not going to use that features. But if you're interested, you can go to this link. Yes?
In this case, where we don't generate rules, n equal to 2 times m doesn't give empty, right? It's no solution.
M does not have solution, so Pm comma n cannot be generated. So it's empty, right? Okay. Well, you can also say, it's like one of the examples that we had before, P1 divided by 0. Okay, so that's empty conjunction, which is top, right? So it's the same thing here. This is empty conjunction in the head, which is obviously true. So Clingo can throw this rule away. Okay, so basically what Clingo can simplify is when the rule somehow instantiate this way, this rule is no longer necessary, right? If the body contains, along with some other atoms, the body contains some bottom, right? Or absolute falsity, the rule cannot be useful. So Clingo can forget about this rule. Other rules are the rules that has top in the head. Okay, so those rules are also useless. It does not tell us to generate stable models. So these two rules can be omitted. And this kind of rule that we omitted is actually this type. Because it's empty head means empty conjunction, which is top. Okay, we already have done the intervals. So what are the answer set of this? P1, P2, P3. Okay, so we can just skip that part. So let me just write here. The answer set will be this. What about this guy? Square 1, 2, 3, square 1, 2, 3. Yeah, so, okay, you're well prepared for the quiz then. So 1, 2, 1, 3, and square 3, 1. Okay, so you can fill all the 9 things. So let me not repeat. The good thing is you can actually run Clingo to verify all these claims. And there's also this. I'll just leave this as an exercise. Okay, so let's think about this. So we want to generate the stable model like this. Can we write one rule program to have this as the stable model? Let's not. Let's give some time to think about. Okay, so anyone has idea? Let's give chance to you first.
P of n m.
P of m n. Okay.
Is m from 1 to 4.
M is 1 to 4.
N is 1 to 4.
N is also 1 to 4.
M is greater than n.
M is greater than equal to n because it also. Yeah, so this is the solution. Good. All right. Another thing, prime. So we saw this before. N is a prime if it is the number starting from 2 to n, and there is no evidence that is composite. Okay. So this was the definition that we saw before. I'm not going to repeat this. So we first defined the composite, okay, and define prime. So prime was defined in terms of composite, and we use this negation as failure. So if you cannot say this is composite, then this is prime. Okay. Now note here that this is another use of stable models with negation. If you just look at the minimal models, you don't actually get the same idea. Okay, because in the minimal model, basically what you have here is actually same as this one. Okay, but what we require here is the minimal models according to this idea of negation as failure. So if you just look at the minimal models of P if not Q, then the minimal models is actually P and Q. Right? But the stable models here will be only P. We only need this guy. Okay? So when we define prime number, we are only looking at the prime numbers that is not composite. Okay? So how do we actually this is all program. Okay? So let me show you. So this is the, okay, let me clear up. So this is the program that you just saw. Okay, so we can run Clingo 5 minus C. So here we have the placeholder n. So let's call n to be 100. N equals 100. And prime. Okay. Okay. So it finds prime number up to 100. Of course, it doesn't take too much of time. Speaking of that thing, so 0.001 second. Let's actually try maybe 1,000. Again, 0.015 seconds. 10,000. 0.4. 100,000. I don't know. So relatively quick, but of course generating prime number is not that simple task. All right, next one, factorial. So how do you find factorial? It's also recursive definition. So fact of 0, 1 means the factorial number, factorial of 0 is 1, and n plus 1's factorial is f times n plus 1. If you have the previous number, so nth factorial is f, then n plus 1 factorial is f times n plus 1, right? So this is a recursive definition of factorial. So here is the, actually I didn't say this, but everything that starts with the percent sign is a comment. So you can just say, Clingo doesn't care about this comment, but it helps you to understand what has been achieved so far. So far you describe factorial to be this way. Now you can actually use the projection idea. So I don't want to know this binary predicate. I only want to have the first n plus 1 factorial. So then I can project this one into this. Now note here that unlike in, note here that we actually use the same name fact for both unary and binary. So Clingo actually allows that. Okay? And this is yet another directive to Clingo. If you just, usually when you ask Clingo, it will find all stable models, all the predicate names will be displayed. But if you use the pound sign with show command, it will only show this predicate. Okay. Okay. So yeah. Okay. So it took 33 seconds to finish 10,000 prime numbers up to 10,000, which is not too bad. So let's actually try the factorial. Yes.
What does this other, like, p-division says, like, solving 0.1?
What is this thing?
So inside the time,
Uh-huh.
there's 3 components, like solving first.
Yeah. Let me tell you later. Okay. Okay. So this is the factorial. Okay. Now, actually, I did comment out one thing. So if I put it back, this will only generate fact, unary fact predicate. Okay. Now the question about these times. So Clingo find this. So I think the solving time. Actually, I don't know exactly what that is. So let's actually go back. So here, roughly, so Clingo can find all stable models, and this is probably not very accurate, but the whole solving actually took 0.13, and check whether there is no other stable model here. It takes 0.13 seconds. The finding first stable model took 0.006 seconds. So I may be wrong. Actually, I don't. Sometimes these times are not really exact. So I usually use time command in the command line utility. Okay, I think this is it for today. So let's start the quiz now.